I will just go ahead and hand over to the next chair for the last talks of today. My fellow Scientific Organizing Committee member, Dr. Pierre Durand, is a researcher in the Evolutionary Studies Institute at the University of the Witwatersrand in South Africa. And Dr. Durand, please take over. Thank you.
Thanks so much, Andrew. And thanks to our speakers thus far. So we have five more speakers to go, and we've moved into the realm from chemical evolution, it seems, to biological evolution, which in itself raises, because we've got a minute or two before Barbara's due to begin, so that raises a very interesting question itself, which was raised at the very beginning of our conference, as to if there's a difference between chemical evolution and biological evolution. What is the difference in living forms between those two? So I found a very interesting article by a biology teacher in the US, Annie Prudhomme-Généreux, whose paper in 2013 entitled "What is Life?" She, in her table 1, gives 120 useful definitions. So that just elaborates on just how difficult philosophically the very first question is. So I guess we're going to be moving into the realm of microbial life. And our first speaker is Barbara Sherwood-Lollar, one of my co-scientific organizing committee members. And she is let me have a look over here, a university professor at a Canada Research Chair Tier 1 professor at the University of Toronto. So thank you, Barbara. Look forward to your talk. Indeed.
Terrific. Thank you. So in some ways, what will be fun, I think, is that this is a rather seamless transition from some of the things that Shino was talking about, but with a slightly different perspective. I purposely tried to make sure that I show you a different angle to some of this deep subsurface microbiology, in particular related to concepts of habitability. So the key differences between what I'll be talking to you about here and the groundwaters that Shino's working at the Cedars are depth. By the time we'll be looking at the things I'll be talking about, we are now 2-3 kilometers deep in the earth. And yet we still have the flowing groundwaters, such as that you see here today. So these are waters that are older, much more cut off from the surface carbon cycle, and I'll show you how we know that. They are like some of the systems that Shino's been describing, driven by water-rock reaction, producing electron donors and electron acceptors. These are similarly very hydrogen-rich environments. Some of the gas phases associated with these fluids are up to 50% hydrogen. In the dissolve phase, that means nanomolar concentrations, 5, 10, 15 nanomolar concentrations of hydrogen, so enormously hydrogen-rich, like the Cedars, like the hydrothermal vents. One of the other big differences, though, is that we do not have the extreme pHs that Shino sees, probably because within these deeper, older systems, the rates of water rock reaction are slower, and so it isn't driven to the same pH extremes. And then as well, there's more diversity of different water rock reactions producing hydrogen. Serpentinization for sure is an extremely important part of what's going on in these systems, and I'll talk a little bit about that. But here we also see the contribution from hydrogen of a process called radiolysis. And this is really driving, particularly recently, some of our thinking about prebiotic chemistry, abiotic organic synthesis in the deep subsurface, and the connection to deep life. Before going on, I just want to take one moment to acknowledge and remember the gentleman you see standing on a ladder in the middle of that photograph. That's 1.8 kilometers underground, and that is our own just recently deceased T.C. Onstad, with whom we did much of the work in South Africa, although I'll be talking today about the work in the Canadian Shield as well. And so
we seem to be still seeing your title slide, though.
We are, that's why, because the pig figure in the middle is T.C. Onstad. So continuing on then. In particular, the outline that I'll be speaking about, as I mentioned, relates to this idea in particular of life within systems that are cut off from the surface photosphere. So chemolithotrophic life, As I mentioned, there are a variety of hydrogen-producing reactions. Sheena was speaking about serpentinization. I'm going to focus more on radiolysis. The other key difference, as I mentioned, although we're much, much deeper now than Sheeno's system at the Cedars, the other key thing is that whereas Sheeno's work were in ophiolites, which are thin subductive wedges of ultramafic material left on the continents, we're working in the Precambrian crust itself. So systems that are tens of kilometers thick. In particular, then, as I showed you in the title slide, this is the type of thing that we're working on. What you see there are naturally occurring groundwaters that are discharging and flowing from these rocks at great depth around the world. These are found in South Africa, the Canadian Shield, Fennoscandian Shield, Brazil, Australia. These are saline, naturally occurring groundwaters that are released from fracture systems within these fluids. And as you can see on the right-hand side in this plexiglass tube where we collected the water, just to show you, these are exsolving large amounts of reduced gases, methane, hydrogen, nitrogen, etc. One of the reasons that we focus in particular on the fluids is because in these ancient rocks, we really want to understand not only the history of life that's in these fluids at this point in time, but we also want to connect that back up to as far back in the Earth's cycle as we can go. So we're very interested in understanding, not only following the water to understand its geochemistry and therefore what it means in terms of the habitability of D life, but also to understand the residence times of these fluids, because that can give us important information about the biosphere that we find within it. We understand whether or not these fluids have residence times on the order of thousands of years, as many of them do, particularly as we get close to the surface. As you go deeper, though, down to about 1 to 2 kilometers, for instance, in South Africa, we see many sites where the residence times for the fluids are millions of years. And down at 2.4 kilometers at one site in the Canadian Shield, we actually see fluids that are billions of years in age. And so by looking at the life associated with each of these different systems, we hope to be able to say something about the timing, the interconnection, and the preservation of life within these deep ecosystems. So understanding the fluids following the water, both for its geochemistry and for the constraints on residence time, is a very important aspect of the work that we've done. As you can see from those ages that I've given you, these are systems that are in intense hydrogeologic isolation. In many of these systems, it has literally been on a geologic timescale that these fluids have been cut off from the surface photosphere. This has implications for the life that we find within it, but it also has implications for the water rock reaction. Because when you have processes like serpentinization or radiolysis going on, the products of those water rock reactions can accumulate over very long timescales. And indeed, that's the part of the understanding for why the levels of hydrogen are so high within these systems, as I mentioned earlier, on the order of 5 to 15 micromolar. Work that we've done over the last 30 years within these Precambrian continents throughout the world essentially was encapsulated in a paper we wrote in 2014, where we took a look at data from all of the sites where we've worked, but also sites where other people all around the world have worked, looking at fracture fluids within these systems. The Precambrian lithosphere of the planet is shown here in blue and green. Blue are the exposed Precambrian rocks, green are those that are covered by Paleozoic cover. But the clear point that I'm making is that Precambrian rocks constitute a major proportion of the continental lithosphere. They in fact account for more than 72% of the continental lithosphere by surface area. And since these cratons are, as I mentioned, tens of kilometers thick, even more by volume. Within that paper, then, pulling together data from all over the world from different groups that have worked on hydrogen, we were able to show that, in fact, there's as much hydrogen production coming out of the continents as there is coming out of the coming out of the marine lithosphere. But prior to about 2014, really, this information had kind of run underneath the radar. A lot of people were working on ophiolites, a lot of people working on the marine lithosphere. This paper tried to pull together and bring attention to the fact that we have a large amount of habitable real estate, fracture waters deep within the continental crust as well, where we see a lot of hydrogen. And as I've mentioned, being produced by serpentinization, which is a process that Shino talked about a lot, but also the one that I'll focus on today, which is radiolysis. The reason we began to focus on radiolysis is shown in the small inset map in black and white in the upper left-hand side of this slide. And that is essentially what that slide shows you are some of the largest accumulations of serpentinite, ultramafic rock on the planet. These are found in particular on the Precambrian continents, and they constitute those black belts you see in that black and white map. All of that black material is serpentinized rock, ultramafic rock. So these are major provinces in which, when we went there, we expected to find hydrogen. We know hydrogen is produced by the serpentinization of that type of mineralogy. But I'm going to jump now down to the center of the map to South Africa, because although, of course, the Bushveld complex and others are areas of ultramafic rock within Southern Africa, the initial set of sites that we worked on with TC Onstad in South Africa were in the Witwatersrand Basin, and most of them were sites that are much more felsic in origin. In other words, we didn't anticipate finding hydrogen there at the same levels, and yet we did. So these rocks full of hydrogen, despite the absence of ultramafics, and therefore serpentinization could not be the explanation for what we were finding within the deep gold mines of the Witwatersrand Basin. To understand then the hydrogen that we found in the Wits, we had to go way back, in fact, right back to some of the work done by the earliest physical chemists and nuclear chemists working at the time of the discovery of radioactivity. And so I highlight here Madame Curie's treatise of 1910, where famously, of course, defining radioactivity from uranium, thorium, and radium decay, but also it's fascinating treatise. If you take a look at it, you'll see there are entire chapters as well of experiments on what she called the effects of émanation radioactive, radioactive emanations. And essentially, they were very, very interested then, not just in radioactive decay, but also in radiogenic chemistry, the effect of alpha, beta, and gamma particles when they impact gases, liquids, and solids. And so there's a variety of very fascinating reactions described in that book in various chapters, and in particular, this radiolytic decomposition of liquid water, known to produce hydrogen and oxygen. And in fact, that turned out to be the key to the Witwatersrand Basin. And in a series of papers that Li Hung Lin did as part of his PhD, working with TC at Princeton, and then also doing experiments with us at Toronto, what Li Hung was able to show is that, in fact, based on modeling, field studies, and experiments within the Witwatersrand Basin at those more felsic sites that we were working on initially, the origin of the hydrogen there was not serpentinization, but in fact, radiolytic decomposition of water in response to these radioactive particles being produced by uranium, thorium, potassium decay in the rock. Since that time, we have looked for life within these fluids all around the world. Life sustained, as Shino showed, by hydrogen produced by serpentinization, but also life produced sustained by hydrogen produced by radiolysis. And indeed, in these sites all around the world, we typically find that one of the dominant microorganisms that's found, one of the dominant metabolisms is in fact hydrogen utilizing sulfate reducers. So having kind of unlocked the key to understanding where all the hydrogen for that deep biosphere is coming from, what we've done in recent years is try to focus on the other part of the problem, to actually try to focus on the aspect of the electrons acceptors within these systems as well. So not just understanding the production of hydrogen from radiolytic decomposition of water, but the origin of the sulfate that those sulfate reducers must be accessing if they're actually going to drive a complete metabolic cycle within the subsurface. This work was done by Long Lee. He was a postdoc with us at Toronto and is now at the University of Alberta. And what Long did was to focus on this idea of radiolytic oxidation, but looking not just at the effects of hydrogen, but the effects on the pyrite minerals within these rocks themselves, as disseminated sulfates like pyrite or fool's gold are very, very common within the mining environments where we've been working. Essentially, what he was able to show is, of course, the other half of this equation. When you break apart a water molecule, is you're producing not only hydrogen, you're producing a whole series of reactive oxide particles. So as uranium, thorium, potassium decay and produce alpha, beta, and gamma particles, the radiolytic decomposition of water then produces not only hydrogen, but also by indirectly oxidizing the sulfide minerals, oxidizes that sulfur and transforms it into sulfate within the dissolved fluids. And specifically then the evidence for that is shown here. What Long did was to take a look at the sulfur isotope signatures, and in particular the presence of the CAP33 sulfur isotope signature. Essentially, he took a look at the rocks themselves, and because they are Archean rocks from 2.7 billion years old, they can have a particular signature of this sulfur isotope. When he measured the water and the fluids, he found that had exactly the same signature. And in fact, it was the first time that a mass-independent sulfur isotope signature had ever been found in anything other than a rock. And Long discovered it within the dissolved sulfate in these fracture fluids, showing us that in fact that sulfur was being oxidized and mobilized from the ancient rocks. And showing us then that we've got a system in which the radiolysis actually provides us with a closed cycle, a system in which the process of radiolytic decomposition of water produces not only the hydrogen, but also the oxidants, and from that, the dissolved sulfate, providing us then with a coherent long-term mechanism capable of supplying both the electron donor and the electron acceptor for all of those hydrogen-utilizing sulfate reducers found within these deep systems. And so these are systems that have been really fascinating to us because they give us important information about radiolysis driving the production of hydrogen, but now also radiolysis driving a deep sulfur cycle. And in the few minutes remaining, what I want to show you is very recent work we've done that's in fact extending that to the production of carbon-bearing compounds by radiolysis in the deep subsurface, and why that has important implications for prebiotic chemistry and astrobiology. Specifically then, if you take a look at the Kidd Creek mine, this is one site in particular where we've been working. As I mentioned, we've worked on sites all over the world, but this one in particular is a very, very interesting setting in which to work. Part of the reason is the age of the rocks, 2.7 billion years in age. Part of the other reason is it is one of the deepest base metal mines in the world, down to 3 kilometers and drilling even deeper. So it gives us, again, an opportunity to take a look at these systems that are very isolated from the surface. I won't be talking a lot about the noble gas results, but this is, as I mentioned earlier, one of the sites where the groundwaters have been shown to be more than 1 billion years in age. So isolated from the surface on very long time scales, but accumulating the products of water rock reaction, such as the high hydrogen and the sulfate, enabling the habitable environment that then sustains hydrogen utilizing sulfate reducers. And we also very interested in this system because of the carbon cycle. Way back in 1993, when we first began to work at this site, and then a series of papers subsequently. This was one of the first deep terrestrial systems where we actually showed evidence of abiotic organic synthesis, and in particular, the production of methane, ethane, propane, and butane by processes like the Sabatier reaction and Fischer-Tropsch synthesis, which you've heard all of the previous speakers talk about. And so I won't talk a lot about the methane story at Kidd Creek at this point in time. Suffice to say, it is related to these processes of serpentinization and radiolysis. But really, that was our first indication that there is an abiotic deep carbon cycle within these systems. Moving on to present day, just now in 2021, we published a series of papers that continued that deep carbon story. In particular, this particular paper down here with title circled in red, where we began to look at the acetate and formate that's associated with those billion-year-old waters. The important thing to emphasize is sometimes when people think about these deep ancient cratons, they have the idea that they're carbon poor. Well, they are carbon poor with respect to labile organic carbon related to the surface photosynthetic driven carbon cycle. But they're not actually carbon poor at all. They contain vast remnants of ancient carbon. And so there are graphitic horizons, there are carbonate fraction minerals. The amount of carbon material in solution is indeed low relative to what is found in the rocks itself. The dissolved inorganic carbon, or DIC, tends to be on the order of 30 to 60 micromolar. The dissolved organic carbon is the subject of the last two slides that I'll talk about. And what's fascinating about that is that the DOC at a site like Kidd Creek reveals a very unusual and very simple organic soup. Essentially, if you look at the total dissolved organic carbon in the fluids in concentration, that's shown here in orange. And then if you look at the total amount of acetate and formate, just acetate and formate, that's shown in blue. And so it shows you that for many of these boreholes, acetate and formate within analytical uncertainty essentially account for all of the DOC. There are trace level organics, but essentially there are only two primary components, acetate and formate. And we see that as well in the isotopic information, which is shown here on the bottom, with isotopic mass balance as well, showing us that for all of these 4 to 5 boreholes that we're investigating 2.5 kilometers below the Earth's surface, the dissolved organic carbon ranges from 2 to 5 millimoles. It's a substantial amount of carbon, but it's all acetate and formate. Two of them alone make up for it, between 50 to 90% of the total DIC. And it's a rather unusual composition of acetate and formate as well. If you compare these fracture fluids to other fluids found associated with other geologic settings, they have very unusual characteristics. Sedimentary basin brines are known to have VFAs, but they typically have very low levels of formate, whereas here we find very high levels of formate. In addition, sedimentary basin brines often have many organic acids, propionate, butyrate, and we simply don't find those above detection limit within Kidd Creek. If we compare Kidd Creek fracture fluids to hydrothermal vents, there too we see substantial differences. Hydrothermal vents are typically characterized by very high levels of formate and much lower levels of acetate. Whereas here at Kidd Creek, we see the opposite. It's always acetate as the dominant compound. Typically, acetate to formate ratios are in a 2-to-1 ratio. The other key point to make is that these Kidd Creek samples are actually at a subsurface observatory, a place where over the last 10 years, 2.4 kilometers below surface, we've been able to return again and again and measure the features of these exsolving fluids. And 10 years of monitoring has shown that the delta C13 signature of the acetate and the formate and the concentrations of these two compounds are completely uniform, essentially no variation over a decade's worth of monitoring, which is in and of itself very unusual. And so a whole variety of unusual features about these systems. As you can see here on the left-hand side, where we see concentrations of acetate against delta C13, this is work by our co-author, Verena Hauer from Bremen, showing a compilation of acetate that she's found from all over the world. You can see how unusual Kidd Creek are, shown here on the upper right-hand side of that plot in red. They're not only amongst some of the highest concentrations of acetate that she's measured, but they are the most C13 enriched ever reported, and very much differ from other deep subsurface sites where the C13 enriched values reflect some of the ancient refractory organic matter in the rock. So for instance, if we move now to the right-hand side, this histogram shows the delta C13 signatures for refractory organic carbon found in rocks throughout the Precambrian rocks of the Canadian Shield. At many sites, we do find acetate, and that acetate has an isotopic composition about comparable of the bulk refractory organic material and completely consistent with a biological carbon cycle. Kidd Creek, as you see here, very, very different. Again, delta C13 signatures between -1 and -5, more enriched than had ever been seen. So a whole variety of features that show us that acetate within these systems and formate within these systems is unlike any that we'd seen before. And in the course of trying to figure out what exactly we had going on here, we're working quite a bit with Bénédicte Menez at the IPGP at the University of Paris, and she alerted us to some fascinating research going on in the physical chemistry literature. This is literature that doesn't often interface with people who are working in subsurface microbiology, but really should. These are colleagues in France who are looking at radiogenic chemistry in the context of understanding what will happen if radioactive nuclear waste is put in the subsurface. And so they're doing a whole series of experiments looking at radiolysis. And in the course of that work, not only are they looking at radiolytic reactions that produce hydrogen, but in a series of reactions where they added carbonate minerals to the experiments as well, they were able to actually show in the course of radiolysis, not only the production of hydrogen, but the production of organic acids, and specifically acetate, formate, and oxalate. Now, there's a very, very early days. The specific mechanisms, the production rates as a function of various alpha, beta, and gamma radiations have not yet been completely elucidated. And to this point in time, we know nothing about the stable isotope fractionation factors associated with these radiolytic experiments. But in fact, through collaboration, we hope to actually bring some of those experiments to light over the next few years as we undertake some collaborative experiments with this team. But the key point is it allowed us to at least begin to understand that radiolysis may not only contribute to deep subsurface hydrogen and sulfur cycles, but may have a contribution to make to the deep carbon cycle as well. And what it allowed us to do is at least do a plausible first order mass balance. From the work by Li Hung Lin, we had estimates from uranium, thorium, and potassium content of these deep rocks of how much hydrogen is produced per year by radiolysis. The physical chemistry literature then had radiolytic rate productions for acetate and formate. And by coupling those two values, we were able to do a first order estimate of just how much acetate and formate we might expect to see in these fluids based on the age of the fluids. So for the Witwatersrand Basin typically has residence times derived from noble gas analysis on the order of tens of millions of years. And indeed, that would predict acetate and formate concentrations on the order of 100 micromole. That's exactly what we see. Moving on to Kidd Creek, where we have these billion-year-old waters, all the way down to waters that are only hundreds of millions of years old, where there we'd predict that we'd expect to see concentrations of acetate in the 1600 to 2700 micromole, so 1 to 3 millimolar. Again, that's exactly the kinds of concentrations we see at Kidd Creek. And so at least on a first order basis, it shows us that these radiolytic reactions are capable of accounting for these very high concentrations of acetate and formate we see in the Kidd Creek fluids. And so early days yet, but this has sparked all kinds of fascinating conversations about the role of radiolysis as one of a variety of water rock reactions that might in fact be supporting a habitable world deep within a planet cut off from photosynthesis. As we've mentioned, this may provide us with insight not only into a subsurface biosphere that's been isolated from its interaction with the surface, but also potentially a window into a prebiotic Earth. I couldn't resist one of TC's quotes. He always talks about, what about a warm little fracture rather than Darwin's small pond? And indeed, it does then provide us with a set of reactions that not only us, but a whole bunch of people working on origin of life are interested in as well in terms of radiolysis. Moving off of Earth, it gives us a model for planetary habitability that might sustain chemolithotrophic life on planets where perhaps photosynthesis never arose. And thinking back to Lisa's talk earlier, it forces us to start to think about what might a biosignature look like if we're not looking for photosynthetic life. What would it look like if we're looking for chemolithotrophic life? And so just to end there with future collisions and directions, again, experiments are needed in order to bring these various interdisciplinary fields together to really get a set of information we can use to interpret what we find in the real world. Modeling is going on by a whole bunch of groups, and they're extending it to other elemental cycles as well in terms of the context of understanding prebiotic chemistry and the origin of life. And I've just written some few references here from some of that literature, but extending on to take a look at the role of radiolysis, for instance, in nitrogen as well. One of the interesting things about radiolysis, I mentioned this earlier, radiolysis is less mineralogically restricted than serpentinization. As I mentioned, serpentinization exclusively associated with mafic and ultramafic rocks. In contrast, radiolysis happens in all rocks. It's a universal driver of habitability and abiotic chemistry because it requires simply the presence of uranium, thorium, and potassium, which are present in all rocks. So there too, a very interesting thing to think about as we think about moving off of Earth to look at habitability elsewhere in the universe. We've already done a couple of papers taking a look at the potential contribution of radiolysis then to the habitability of Mars. That's the work of Jesse Tarnas that's been highlighted here. It's work with Jack Mustard. And again, a variety of groups, some of whom were cited earlier today, then looking at the role not just of serpentinization, but also of radiolysis in the context of understanding some of the other ocean worlds, such as Enceladus and Europa. One of the things about radiolysis is that it does not drive us to assume we must have a certain range of pH, whereas serpentinization is more restricting that way. And with that, I just want to end and thank the various people who have contributed to the talk that you've heard today. A lot of this work is taking place under the CFAR, which is the Canadian Institute for Advanced Research in Canada, and a group that I'm co-directing with Jack Mustard called Earth 4D, Subsurface Science and Exploration. And that just gives you a picture of some of the various people associated with that team. And with that, I'd like to draw this to a close, and hopefully at the 30-minute mark, I think, and happy to take the next time available for any questions and Q&A. Thank you.
Thank you so much, Barbara. That's amazing. Just a reminder to our listeners to please, if you want to pose a question, type it into the Q&A at the bottom of your screen. So, Barbara, how deep do the deepest microbes have they been found? Do you find any microbes 3 kilometers down?
Yes, that one slide I showed you was specifically from the fluids of Kidd Creek. If you go to South Africa as well and other places around the world, so far, life has been found. As Steve said earlier, life finds a way. So far, life has been found in almost all of the places that we've looked, unless there's obvious barriers. For instance, the thermal limits to life work that Fumio Inagaki, Kai Heinrich, and others have done on a drill in the Nankai Trench showed crossing an obvious thermal limit, and below certain high temperatures, then the signs of life disappeared. But in any other areas such as these, where we don't have a pressure limit to life, we're not close to the thermal limit to life in the present day, life has been found. Now, sometimes that's taken a while. The salinities of these fluids are very high. Because of all of that water rock reaction, the salinities of these fluids can be up as high as 180 milligrams per liter. So up to, in some cases, 10 times the salinity of seawater. And that causes some issues for routine metagenomic analysis. As well, the cell counts tend to be very low, on the order of 10 to the 2 to 10 to the 3 cells per mil. So that can cause some problems as well. So the off-the-shelf kits to just quickly go down and take analyses can sometimes come back with false negatives. It takes quite a bit of work to actually refine the techniques to deal with the various challenges associated with these very deep, very saline fluids. But we've certainly been able to find it from culturing results, from some of the 16S work that's been done. And then Shino herself has graced us with her presence, come down with us to 2.4 kilometers below surface. And she's currently working on metagenomic data from these Kidd Creek systems. So we're very much looking forward to that.
Do you suspect all of these to be archaea? So far, once you've from the data that you have,
no. In fact, these have been found. No. In fact, if you take a look across the whole world, and again, we're not the only people doing this work. This is a very robust field at this point in time. And so, if you take a look at the work that's coming out of, just to name some places that are independent teams, there's work going on in Finland and in Sweden. There's work in South Africa, of course, as I mentioned. There's a whole variety of ecosystems that are found. Now, there are some patterns. As you go deeper, you're typically moving into lower biomass, less biodiversity. And so we do see differences, more chemolithotrophs at depth, but nonetheless, biodiversity. There is a range of microbial metabolisms throughout all of these systems, and there are abundant bacterial as well as archaeal systems. In some places, and again, this is why follow the water is so important, we cannot assume that the organisms are the same age as the rock. The fluids are the critical aspect. The fluids will determine the residence time of the fluids, which I didn't talk as much about this time because I think last time I talked about it quite a bit. It's why the residence times of those fluids are so important. They can give us an age estimate of the last time that the fluids were connected to the surface. So that's important to give us a sense of how long those organisms have been down there. And typically, those groundwaters may be old, but they're not as old as the rock themselves. So for instance, at Kidd Creek, the rocks are 2.7 billion years. The fluids are between about 1 and 1.5, which is still really exciting, but not as old as the rocks. And obviously, the life could be as young as the youngest drop of water. So in order to really understand and constrain the timing of when those microbial ecosystems either penetrated those rocks or developed within those rocks, we really need to understand the water. And we need to understand three things. We need to understand not only the mean age of the water, but to try to constrain what the oldest drop and the youngest drop might be. So it's a complicated set of parameters, but it's extremely important to understand when we're talking about deep life. You need to know about the rock, you need to know about the life, but you need to know about the water, because that's the median that has moved life through those systems, and that will provide us probably with the best constraints of just how old the microorganisms are. But we cannot simply make assumptions that the organisms found are always the same age as the rock.
Yeah. Gosh, amazing, fascinating stuff. Thank you. I'm looking at the other questions of if there are any other questions coming up over here. I don't see anything else. David, shall we carry on? Yeah.
I think Steven Zinder has a question. Bubble to the top.
Oh, hey, Steve, how are you?
He's muted, unfortunately.
Yeah, no worries. We collaborated on very near surface microbiology a few years back.
I know, Pierre, if you want, so I can read the question. The question is from your diagram. From your diagram,
yeah, I can't seem to see it.
Okay. From your diagram, H2, Formate, and Acetate should be electron donors for sulfate reducers, but their stability indicates that nothing's happened or nothing's happening. Any ideas why?
Exactly. At the moment, we're really trying to dive into a whole variety of modeling approaches to try to understand that. Clearly, there's a variety of things. It could simply be that within the mix of organisms that we're looking at, there are not, and we certainly don't see the in the MPNs, in the culturing work that we did not see a positive response for any of the microbes that would be using acetate or formate. That's not too surprising. There's always the possibility of false negatives. We did see a lot of response from hydrogen-utilizing sulfate reducers. So there's always the possibility that there simply are not organisms within this particular site and environment that are using those compounds. And the other possibility, of course, is they're additional rate limiting steps. Third possibility, they may be using it, there may be a cryptic cycle. In other words, they may be using it at very, very slow rates. That's not unknown within these deep subsurface environments. Similarly, if you look at methane, you see methane isotopic signatures that are indicative of its abiotic source. But there are methanogens and there are methanotrophs. We know this from clumped methane isotopes analysis, but we had to go to a very sensitive technique like clumped methane isotopes to see that cryptic methane cycle, because simply the methanogens that are there are very low in number. They're turning over the methane pool at very, very slow rates relative to the very large amount of methane that's produced. So we can't rule out entirely the presence of microbes that are using acetate and formate, but what's clear is that they're not doing it at any kind of a rate that's impacting the bulk pool that we see. And I think that's what's fascinating about these environments. You know, in surface environments, we may have systems in which the microbiology is running so fast, it's dominating, and therefore we don't see much abiotic organic chemistry. These systems are at the opposite end of the spectrum, where the abiotic organic signatures are dominating because life is taking place at such a small rate. And so it's a fascinating expression of this whole idea of thinking about the signal to noise ratio when we think about what we might be looking for on other planets. And then I think Shino's system is somewhere in between the two. And it just really emphasizes why it's so important to take a look at a spectrum of different sites, because we're going to see different things that will give us different answers about how we go about then translating some of these search for life techniques to other planets. I sometimes refer to life as us looking for an abiotic needle in a biologically dominated haystack where life has overprinted everything. But if we go out to other planets and moons, it'll be the opposite. We'll be looking for the biological needle in an abiotic haystack.